Collection of videos related to amateur radio antenna. Topics covered are Yagi-Uda antenna, inverted V antenna, folded dipole antenna, half-wave dipole antenna, delta loop antenna, SWR, and antenna tuner. Yagi-Uda antenna is often called just a Yagi antenna. It was invented in 1926 and consisted of a driven element, a reflector behind the driven element, and directors in front of the driven element. In case of amateur radio, ham radio, the driven element is connected to the transceiver. Yagi antenna was a common sight on rooftops of houses earlier when they were used to receive television stations before cable and satellite TV became popular. Reflector and directors are called parasitic elements. Reflector is usually 5% longer than the driven element, while directors are shorter. Yagi antenna has a much higher gain and directivity than a simple dipole antenna. Gain is usually about 10 dB. Gain increases as the number of directors increase in a decremental fashion. Reflector can give a gain of about 5 dB, while directors can add 1 dB and lesser. The interlinking rod is called as boom. Inverted V antenna is very popular among radio amateurs, especially the beginners, as it is very easy to put up and has a fairly good performance. As the name implies, it has an inverted V appearance, with the two limbs of the antenna forming an inverted V, with the apex at the tip of the non-conducting mast. As the horizontal dimension is lesser than that of a horizontal half-wave dipole antenna, it is useful when there are space constraints. Though theoretically the performance of a horizontal dipole and inverted V are similar, practically it can be lower for the inverted V. This is because of proximity to the ground, effect of ground conductivity, and end effects. Elevating the antenna higher above the ground can improve the performance of the inverted V, though it may not always be possible in a given location. In a folded dipole antenna, a half-wavelength conductor is folded into a longitudinal loop and fed at the center. It has a higher impedance of around 280 ohms compared to the 70 ohms impedance of a horizontal half-wave dipole antenna. Hence, while a coaxial cable is suited for a horizontal half-wave dipole antenna, a twin-lead transmission line with about 300 ohms impedance is used for a folded half-wave dipole antenna. Half-wave folded dipole is commonly used as the driven element of a Yagi multi-element antenna. Like a half-wave dipole antenna, the folded dipole is also resonant and radiates well at odd integer multiples of half wavelengths. As mentioned in case of half-wave dipole antenna, it acts as a 3/2 wavelength dipole at 3 times the fundamental frequency. Folded half-wave dipole antenna is preferred when the impedance has to be higher. Half-wave dipole antenna fed at the center is the commonest type of dipole antenna, and its length is almost half of the wavelength of the frequency for which it is meant. So, the total length of a half-wave dipole antenna for the 40-meter amateur radio band will be almost 20 meter. The space needed for the antenna increases as you go down along the amateur radio bands. I had the opportunity to use both 40-meter and 80-meter half-wave dipole antenna earlier, but I'll have to struggle to get even a 20-meter half-wave dipole antenna up at my current location. Maximum radiation from the half-wave dipole is perpendicular to the conductor with almost zero radiation along the axis of the conductor. This would also mean that it would act as an omnidirectional antenna if installed in a vertical position. But installing half-wave dipole in a vertical position would not be easy for a lower amateur band. In my earlier days of ham radio, I used to simply tie the half-wave dipole across two tall coconut trees using plastic twisted flex threads. Threads would be tied to stones and flung up on top of palm leaves and pulled up in a pulley-like fashion. Of course, those half-wave dipoles used to sag in the center due to the weight of the connecting coaxial cable, and it would be almost a V antenna. A half-wave dipole antenna can also be used at odd multiples of its fundamental resonant frequency. Thus, a 40 meter or 7 MHz half-wave dipole can be used for 21 MHz but not for 14 MHz. It will act as a 3x2 wave dipole antenna at 21 MHz. The directional gain of a half-wave dipole antenna at the resonant frequency is about 2 dB. Delta loop antenna is a full wavelength antenna in the shape of the Greek alphabet delta. The antenna forms a delta shape with limbs like an equilateral triangle. Though it can be made with base at the top, bottom or sides, practically it will be easy to have the base at the top as shown in the picture below. It will need a 4:1 balance at the feed point for impedance matching. Otherwise, the SWR, standing wave ratio, will be high. As with the half-wave dipole antenna, a delta loop antenna for 7 MHz will also function well with the odd multiple frequency of 21 MHz. On 14 MHz, the antenna impedance is high and SWR will be high. For the center of 7 MHz amateur radio band with frequency of 7.1 MHz, the length of the delta loop will be 43.14 meter. Delta loop antenna is fairly easy to construct if you can put up two strong poles. Recommended height is above 18.3 meters for a 40 meter antenna, which comes down to 4.6 meter for a 15 meter delta loop. Standing wave occurs when there is impedance mismatch between the transmission line and the load, which is the antenna. When there is an impedance mismatch, part of the signal is reflected back to the transmitter. This reduces the effective power transmitted and thereby the efficiency. Standing wave can be considered as a resultant of forward and reflected waves together. Standing wave ratio, or SWR, is the ratio between the maximum and minimum amplitudes of the standing wave. Highest level of SWR occurs when the antenna is not connected, open circuit, or when there is short circuit in the transmission line. SWR can be in terms of voltage, known as voltage SWR, and current, known as current SWR. Usually, it is the voltage SWR that is measured using an SWR meter. Ideal SWR is 1 and high SWR above 2 can cause heating of the transmission line and final power amplifier of the transmitter circuit and likely to cause severe damage. Antenna tuner is a device used to match the output impedance of the transceiver to that of the antenna. Optimal transfer of power occurs when the antenna is tuned to the frequency with a low standing wave ratio, or SWR. When the antenna is mismatched, there will be high SWR leading to low radiated power and heating up of the final RF power amplifier as well as the feeder coax. It is always better to have good matching of the impedances without the antenna tuner, and antenna tuner being used to adjust minor mismatches. My friend used to tell that with an antenna tuner, one could even load the signal to a window grill, but the radiated power will be low. This also occurs when one tries to use a 14 MHz antenna for 7 MHz or vice versa. You can use a 7 MHz half-wave dipole for 21 MHz, which is an odd multiple harmonic frequency. Most of the current day transceivers are built for an output impedance of 50 ohms. Many of them also have a built-in automatic antenna tuner. They also have automatic power output reduction mechanisms to reduce power in case of mismatch to avoid damage to the RF power amplifier. Antenna tuner circuits of handheld VHF-UHF transceivers have to work only on a narrow range of frequencies, unlike the HF, which needs to work on a high range of frequencies. An SWR meter is useful along with antenna tuner to look for mismatch and adjust the tuning in case of mismatch for HF transceivers. More detailed information can be provided by antenna analyzers or impedance bridges. A remote antenna tuner attached to the antenna will be more efficient than one attached to the transceiver, but technically more difficult to implement.